All right, well, let's see here. We'll start our recording here. So now we you know in the previous recording I did on section 8.3, the first recording, the first lesson, we went into some detail about uh, the integral test and the comparison test. And now what I want to do is I want to look at a few examples to see whether the series converge or diverge. So take a moment to copy these examples down. Okay, so let me ask you this first series, here, um, can the denominator be factored in this first series? The series n equals 1 to infinity of 5 over 2n squared plus 4n plus 3. So I'm asking, can that be factored? That's like, you know, something times something. Well, we would need a 2n, we would need an n, but I don't see how we're going to get the 4n in the middle, because I either got to have, like a +1 here and a +3 there, or vice versa. So what do you think? Oh, well, you're close, Tina. 2n, Tina said, and Tina said it could be, could it be 2n plus 3 times n plus 1? Could it be that? Right, you get 5n in the middle. So what I was going to say is, I was thinking maybe I could write that series as a telescoping series, but I can't. So it's not a nice series. It's not really a very nice series. I mean, it looks very nice, but it's difficult to work with. Now, in advanced course, you might be able to work with that kind of series, but this one's difficult at our level to work with because it's not a geometric series. It's not a telescoping series. It doesn't resemble any series that we've seen. And we can make the same comments also about the second series. It doesn't really resemble any like easy series, when I say series that we've seen, I mean, I'm talking about series like geometric series, harmonic series, or telescoping series. But what we're going to do, we still can try to see if the series converges or diverges. We can still test for that when we're going to use the comparison test. And let me show you how we work out part A. So, okay, I say for n greater than or equal to 1 because the series starts at n equals 1. This term, 5 over 2n squared plus 4n plus 3, would be less than 5 over 2n squared. And incidentally, both terms are positive. So what I'm trying to do is remember that let's see here. Remember the comparison test. There was a sequence AN and a sequence BN. Well, this would be my AN, and this would be my BN. Okay, so if I let me just I know you're taking notes, but let me just flash back to the that comparison test in your book. Let's see, where is it? There it is. So you have to have a series. You have two series. One is for a series based on a sequence AN of terms, and a second is based on a sequence BN of terms. In our problem, we have to identify AN and BN, and that's what I'm doing here. So, I mean, I know what AN is because that comes from the series, and I want to compare it to an easier term. Well, the sequence of terms, the AN sequence of terms, the AN sequence term by term would be less than the BN sequence term by term, because you know, the denominator here. I mean, this is what makes the problem hard, right? Is the denominator. 2n squared plus 4n plus 3, that denominator is greater than 2n squared. So this inequality has to be true. And this term here, 5 over 2n squared, I had to come up with that. Okay? That's what you have to do with the comparison test. You have to come up with a good sequence that you can compare the quote tough sequence to. Why do I like this sequence? Well, let's take a look. Let's take a look at the series from n equals 1 to infinity of 5 over 2n squared. Well, one thing I'm going to do is we know that the constant 5/2 can be factored out in front. So that'll give me 5/2 times the series n equals 1 to infinity of 1 over n squared. But already I know that series converges. This series here is a convergent series because it's simply a multiple 5/2 of a convergent P series, right? This here is a P series where P equals 2, 2 is greater than 1, so that series converges. All right, and so since that series converges, that's the larger series. Okay, that's the larger series. So the smaller series, which is the series we're interested in, has to converge. If I'll go to the next page here. But may I go to the next page? Is everybody copy down what they need to here? Okay, all right. Okay. Thank you, Tina. And we'll make sure Tyreek's good too before we move on. All right, very good. Well, all right, so by the comparison test, if the larger series converges, and it does, the smaller series also converges. Because when we say the larger series converges, we're saying its sum is finite. Okay, well, if its sum is finite, then the series with smaller terms would also have its sum would have to be finite. I mean, it makes sense, right? If something bigger is finite, something smaller would be finite too. All right, take a moment to copy that down. Let me know if you have any questions. Okay, are there any questions at all? Are there any questions at all on this problem? Yes, I agree. I agree. It does make more sense having an example. And generally, I like to have, I think examples reinforce theorems. So, but sometimes, it's helpful to sometimes look at the theorem ahead of the example too. I try to do it whatever is the simplest way. In math, we try to make things, we take complex ideas and try to make them understand them. And if we can do it in a concrete way, that's, break down the process. All right, let's go to the second series. Again, here's the second series. And, just sort of using your intuition here on this second series, when n is large, the terms of the series, okay, are they going to be affected much by this -1 in the numerator? No, definitely not. What about the +1 in the denominator? Is that going to affect the denominator much when n is large? No, it certainly will not. It certainly will not. So really, when you look at this series and you think about that, you can focus your attention on the n squared over 3n to the fourth. I'm talking in an intuitive way. So n squared over 3n to the fourth reduces to what? What does n squared over 3n to the fourth reduce to? One over 3n squared. Oh, that's a p-series, right? So it makes me think maybe I can compare this sequence of terms that the series is based on, maybe I can compare it to some kind of p-series. I like using the comparison test with p-series because I mean, I know how p-series behave. I know that p-series converge when p is greater than 1, and they diverge when p is less than or equal to 1. The trick is getting the right comparison and making sure you can do it. So in this problem, for the solution, what I do is I don't just do the comparison in one step. I do it piece by piece. Try to do it piece by piece. So like for instance, that first of all, when n is greater than or equal to 1, the terms, well actually when n is greater than 2, the terms of the series are all going to be positive. But when you know, n squared minus 1 is less than n squared in the numerator. So this means then that n squared minus 1 over 3n to the 4th plus 1 would have to be less than n squared over 3n to the 4th plus 1. Sorry, I did a little mosquito there. All right. Now, so that establishes this inequality. But again, the goal is to get to that 1 over 3n squared, right? That's what we want to get to. Well, I know that 3n to the 4th plus 1, that denominator is less than 3n to the 4th. So that means then that n squared over 3n to the 4th plus 1 is less than n squared over 3n to the 4th. Certainly is. And n squared over 3n to the 4th reduces to 1 over 3n squared. So this means then that, let me get that. Yeah, n squared minus 1 over 3n to the 4th plus 1 is less than 1 over 3n squared. Okay, but we know that the series from n equals 1 to infinity of 1 over 3n squared, that's a convergent p-series because p equals 2. And so our series has to converge. Our series, which is smaller, the series where n equals 1 to infinity of n squared minus 1 over 3n to the 4th plus 1, that series has to converge. Okay, that's how, I mean, that's, hold on, let me close my door. All right, thank you. Are there any questions? Any questions on that? Okay, so that's using the comparison test. So let's look at a few more. Let's look at a few more examples here. May I go forward here? I'd like to get at least another example in. Okay, all right. All right. Let's look at these series here. Okay, let me give you a moment to copy it down. Copy the example down. Okay, so, all right, we want to determine whether the following series converge or diverge. Okay, so let's see here. All right. So this series here, well, let's see. Does this -1 matter much when n is large? It doesn't. So if we were to ignore that -1, okay, and focus on the rest of the series, this part here, what would this series act like when n is large? Ah, that's right. Very good, Tina. A geometric series. It's going to act like a geometric series. Okay, and we could try to compare this, and it would be a convergent geometric series, because what's the common ratio? What's the common ratio? What would the common ratio be for the geometric series? Okay, what do you think? Tina has an answer. Let's see if that's right. That's right. Michael has an answer. It's going to be a half. All right. So you have to be very careful with these kind of problems, because like in WebAssign, a lot of them are multiple choice. And does it converge or diverge? And it's either credit or no credit. And you have one chance to get it right. So you have to be careful before you answer the questions, and you have to think carefully. Well, all right, let's go ahead and try a comparison. So I know that for n greater than or equal to 1 over 2 to the n minus 1 power would be greater than 1 over 2 to the nth power. Because 2 to the nth power minus 1 in that denominator is less than 2 to the nth power. So this inequality holds. And this is the comparison that we have to do for this particular series if we want to try to use the comparison test. Are there any questions on the inequality here? I'll make sure everybody's comfortable. All right, so we know that the series from n equals 1 to infinity of 1 over 2n, we know that that is a convergent series, because this is a geometric. It's geometric, and it has a common ratio of a half, which is, you know, less than 1. But we have a problem. We have a problem. The fact that this series converges does not give us any information about the convergence of the series we're interested in. Why would that be? I mean, why would that be for this problem? Well, here's the problem. Here's the problem. And actually, if we again, just see here. Yeah. I think you agree that the geometric series, the sum would be smaller than the sum of the series that we're interested in. Okay? By virtue of the fact of our inequality here. The terms of a geometric series, or the terms of that, the sequence, the geometric sequence, are smaller term by term than the terms of the sequence that we're interested in. And so the series, our series, its sum would have to be greater than the sum of the geometric series. But the fact that the smaller series is finite doesn't tell you about the sum of the larger series. It could be finite, sum of the larger series, but it could be infinity too. So we can't use the comparison test on this problem to establish convergence or divergence of the series. The comparison test gives no information. No information. So we have to try something else. All right, are there, and we are going to try something else, but are there any questions so far? You have to let me know if you're uncomfortable. Okay. Let me see, Rodrigo. I'm sorry. Is it because of the power of n? No. Well, no. You mean why this is true down here? What I'm talking about down here? Yeah. Well, the problem is we agree that this series here, the smaller series, converges. But the bigger series, which is our series, we can't say if that series converges or not because its sum is larger than the sum of this series is larger than the sum of that series. So we can't establish if the larger series is convergent or divergent. Because a divergent series, the sum is infinite, right? For the section 8.3 problems. So, you just can't establish convergence or divergence. Okay. But remember what we said originally. We did say that when n is large, this series here should behave like a geometric series, a convergent geometric series with a common ratio of a half. And in fact, we're going to use that. We can't deny that. The truth is the truth is the truth. So we're going to apply another test here. Let me show you here. Let me bring up the ebook. We're going to apply another test, okay, called the limit comparison test. Let me show you what that test is. Yeah. This is the limit comparison test. Limit comparison test says that if you have two series and you look at the ratio, of the terms of those two series and take the limit. If the ratio of those terms approaches a constant, okay, then the series will either both converge or diverge. Essentially, you're saying that the terms of the one series is in proportion to to the terms of the other series as n gets large. So the one series has to behave like the other series when n is large. So therefore, if one series converges, the other series converges. If one series diverges, the other series diverges. Okay, that's called the limit comparison test. All right, so are there any questions on that before we get back to the example? All right, well, let me get back to the example then. Hold on here. Okay, so what we're going to do is, since the comparison test did not work, use the limit comparison test. And incidentally, we can't use the integral test easily on this. If we, the integral test would be another option, but it's not so easy to use on this particular series. I mean, what I'm trying to say is, for the integral test, what you do for the integral test is you would have, hold on here, you would be looking at the integral from 1 to infinity of 1 over 2 to the x power minus 1 dx. That's what you would be looking at. But that integral is not, offhand, I don't know how to integrate that. I don't know what would work. So, I want to do what's easy. So I'm not going to use this approach. I'm going to use the limit comparison test. So I'm going to define my a sub n term as 1 over 2 to the nth power minus 1, and b sub n is 1 over 2 to the nth power. And what I do is I look at the ratio of the nth term, a sub n, to the nth term, b sub n, and I look at the limit. Okay, I look at the limit. And of course, to just bring this back here. To make my life a little bit easier, this complex fraction, I'm going to multiply the numerator and denominator by 2 to the nth power. And so when I do that, we're looking then at the limit as n goes to infinity of 2 to the nth power over 2 to the nth power minus 1. And then that, if I multiply the numerator and denominator by 1 over 2 to the nth power, okay, if we did that, let's kind of make that a little nicer. I can if I did that, then my expression would reduce to this. And clearly, the limit as n goes to infinity of that expression equals 1. You got out a constant. So this basically means, since the constant's 1, okay, it means that the series, R series, behaves just like a convergent geometric series with common ratio of half when the terms of the series are large. Okay. All right, are there any questions? May I go to the next page? Okay. So this means eventually the two series are very similar. So the fact that the geometric series converges means that our series converges as well. I mean, I'm adding a lot of, I don't know, I mean, I'm trying to sort of, based on experience, I'm trying to share with you what goes on in my mind, when I do these problems. I'm trying to give you an intuitive feel, as opposed to just, applying a formula. Do these words, are they helpful for you? Are they helpful for some of you? Okay. Thank you, Tina. Thank you, Rodrigo. Good, good, good. A number of years ago, a student told me that they found that chapter 8, on series, was the hardest chapter in the book, and it occurred to me, well, maybe I can help my students if I give a little bit of an intuitive feel to the problems, because then maybe it won't be the hardest thing. Okay. All right, let me know if you have any questions before we go to the other one. Tina, is it important that the limit approaches 1? The limit can approach any non-zero constant. Any non-zero constant. It doesn't have the limit of the limit comparison test, so long as the limit of the ratio of the terms approaches a constant, then you'll be okay. Like for instance, for example, if you had let's say on our original series, oh, I'm sorry. Well, the constant is a positive constant. Yes, the constant would be a positive constant. Let's say, like on the original series, let's say that you had, instead of a 1 here, let's say you had a 10. Okay, so let's say our original series was 10. The sum where n equals 1 to infinity of 10 divided by 2 to the nth power minus 1. What would the ratio test, what would the limit comparison test give you when you take the ratio of this term here to this term here? What would the limit comparison test give you? As what number would the limit go to if you take the limit of the ratio of those terms? So the only thing I did was I put a 10 here. I put a 10. Instead of a 1, I have a 10. The limit's going to go to 10. The limit of the ratio of the terms, Tina, is going to go to 10. That just means that the terms of this series here, they're in proportion to the terms of that convergent geometric series. They're just 10 times greater, but they still are in proportion. So they act the same way. It's just they're 10 times larger, the term. That's all it means. As an example. Okay, let's go back to here, the next example. So here, well, let's take a look at this series here. We have 1 plus a third plus a fifth plus a seventh plus a ninth, and so forth. And we could write more terms of the series. What do you think would be helpful to have on this problem, on this part B? What would be like really helpful? A function. That's right, Michael. Let's figure out what the formula of the series is. Let's figure out what the formula of the series is. Okay, well, if we go and write out some terms, well, we have terms written out. This series is going to equal the sum where n goes from 1 to infinity of 1 over 2n minus 1. Okay? Because 1 is the same as 1 over 2 times 1 minus 1. The third is the same as 1 divided by 2 times 2 minus 1. The fifth is the same as 1 divided by 2 times 3 minus 1. So I think you get the idea here, you know, this. And what we're going to do is we're going to use the limit comparison test. We're going to use the limit comparison test. So,
I'm playing, bro.
Here's our nth term is 1 over 2n minus 1.
I'm saying no from now. I don't give a fuck if this nigga paying or not for.
Oh, not now. You're on the. We can hear you, just so you know. We can hear you. Okay, and then b sub n is 1 over n. So what I'm trying to do is I'm trying to use the limit comparison test for this series with a harmonic series. Okay, and so I apply the limit comparison test. I'm going to multiply top and bottom by n over n. And so I got the limit as n goes to infinity of n over 2n minus 1. But then I multiply the top and bottom by 1 over n. Anything to get it in easier form. And we're going to get out 2. We're going to get out a half. Okay, Sergio. Well, don't worry. This will be in the recording. This will all be in the recording. But thank you for letting me know. Thank you for letting me know. Okay. And, you know, the attendance, there's enough. I mean, of course, I love it when people have 100%, right, on their attendance. And you know, that means you're present for 75% of the class. But, you know, if because power goes out, you don't have a perfect like 100% attendance, I understand that. You know, power might go out once for everybody, you know, during the semester. It went out for me one time, but I got back in pretty fast. You know, I didn't miss. I mean, I was lecturing, but I didn't miss much because when I lectured, because I just went back in. But
I swear, I'm telling you, let it be 5. You're not sending me. I'm calling your mom. I'm tired of you.
I'm sorry, not now. What?
I'm tired of your shit. By the time it's 5, you don't call, you don't send it. I swear, I already sweared it. I'm calling your mom, bro. I'm tired of your shit.
Oh, not now. We can hear you.
Sorry.
That's okay. So, okay. All right. All right. Okay. Well, then let's see what this means. So we got a half. That's a constant greater than 0. And so this means, what's this mean then intuitively? It means that our series eventually behaves like 1/2 times the harmonic series. Because remember, that little -1 in the denominator, doesn't matter much when n is large. So this series is going to basically, the terms are going to behave like 1/2 times the terms of a harmonic series. But we know the harmonic series diverges, so therefore our series has to diverge. Okay, so are there any, I mean, really that's really, you know, I mean, basically this is I like having an intuitive feel. I do. I think you do too. Yes, Tyreek, question.
I'm confused how it diverges. Could you explain that?
Well, the harmonic series, um, we had mentioned last time, we talked a little bit about the harmonic series. But I'll tell you what, I'll bring the whiteboard up. Let me see, is anybody, I mean, may I bring the whiteboard up? Does anybody need just a little more time to copy this information? Okay, all right. Let me see here. I can actually do it while people are copying. So Tyreek, you know, the harmonic series is this series, and if we write some terms out, all right, what we're going to get 1. What's the next term, Tyreek? If you want to answer, you don't have to, but I don't want to put you on the spot. But what would the next term of the 1
over 2.
Yep. Good. What's the next term?
1 over 3.
Good. Next term?
1 over 4.
That's right. Do one more.
1 over 5.
Right. And it keeps going, right? It keeps going on and on. Keeps going on and on and on. Now, the terms of this harmonic series here, what are the terms? Are the terms getting smaller as n gets larger? Right. And what do the terms approach as n gets large?
Infinity?
Well, you have a half, a third, a fourth. All right, the terms are approaching 0. But the fact that the terms are approaching 0, I mean, some people, you know, would think, oh, terms are getting smaller. This series has to, terms are approaching 0. This series has to converge. But this harmonic series does not converge because the terms of the series, yes, they're approaching 0, but they're not approaching 0 at a fast enough rate for the series to converge. Okay, so that's why we say the harmonic series diverges. It's an interesting scenario, you know, because I mean, 9 out of 10 people would say that, you know, if I wrote, you know, 1 plus a half plus a third plus a fifth plus a third plus a fourth plus a fifth plus a sixth and so forth, and I said, does this series converge? They're going to say yes. But it doesn't converge, it diverges because the terms of the series don't go to 0 quickly enough. Just like with an improper integral, if you have the integral of 1 to infinity of 1 over x dx, okay, section 5.10, improper integrals. If you have that improper integral, that improper integral diverges. So even though when you graph the function, you know, you graph the function is getting close to the x-axis, and the area is getting like smaller and smaller in the tail, it still doesn't converge. It's infinite area. It's the same kind of, you know, if you can appreciate that, then it's the same kind of thinking for the harmonic series. Does that help? Does that help you feel a little more comfortable, Tyreek?
Yeah, I was also asking, like, how do we know if it's approaching zero quickly?
Well, that's why we have these tests. We know, like a geometric series, a convergent geometric series, the terms of that series have to approach zero, but they approach zero in a geometric rate. Have you ever heard of like arithmetic growth and geometric growth, or arithmetic decay and geometric decay? Geometric decay, like exponential decay, will that's like a geometric series. And so it's because you're taking a number and raising it to a power every time, and it just goes to zero at a fast enough rate to converge. But right, I mean, the thing is, you see, what we do is we take these series. It's a very good question. I know there's another person who had a question. I'll get to that question. But these series, you see, what we try to do, the ones that are complicated, and you know, you're going to see a lot of ones that are a little bit complicated. We try to compare those complicated series to series that we know something about, like a geometric series, a P-series, a harmonic series, you know, or we try to use the limit comparison test, where we also use essentially make a comparison with the complicated series to a series we know something about. Geometric series, harmonic series, P-series. We all know what those series are going to do. And that's but the question is, so you have to come up like in this problem here, when we let b of n equal 1 over n, right? So you knew that a of n was equal to 1 divided by 2n minus 1. You knew that. The question is, how do we find b sub n? How do we find b sub n? Well, what sort of helps me is I say, as n gets large, this little minus 1 here isn't going to affect the terms of my series. So, I could have just as easily chosen 1 over 2n here for b sub n. I could have done that, but I just chose to use 1 over n because harmonic series, you know. So that's really the challenge, is finding out, you know, what your other series is going to be where you're making the comparison. But if you just remember, usually it's going to be a series where, you know, where like a harmonic series, a geometric series, or a P-series. Those are our favorite choices. Okay, does that kind of help you feel a little better? I mean, once you get some practice, you'll feel real good. But all right, thank you, Tyreek. And let me see, there was another question here. Oh, okay. I think, all right, we got that. Are there any other good questions here? Okay, let me stop the recording.